now. So when we deal with constraint optimization, so previous things we had this, we talked about a few methods by which we can solve an unconstrained problem. So these are continuous functions. We have to understand these are continuous and differentiable functions. So anything that we said in the previous section and in this section applies only to continuous and continuously differentiable functions, really. It's important that we stress that these are continuously differentiable functions with possible discontinuous points being just, you know, that we can easily detect when there are discontinuities. For instance, that, you know, okay, we can deal with stuff like a function that is the absolute value of x, for example, because it is continuous, it is differentiable except for one point at 0 at which it doesn't have a derivative, because the derivative is -1 and then it just immediately jumps to 1. So it doesn't have a derivative at 0, but we can deal with that as long as we can easily identify those points and take a look at those kind of points separately. And in this chapter, we will discuss a sort of conditions that, given that the functions that we are dealing with, so there will be functions pertaining to the optimized function, the target function or the cost function. In the previous section, there was only the cost function. There was no other function involved. But in this section, we assume that there are other functions that work as the constraint functions. And the constraint functions in this section, we assume that there are two kinds of constraint functions. So there are functions which says that some g of x is smaller than or equal to 0. So we assume that it's smaller than or equal to 0. It could be smaller than or equal to some constant, but then we can always rearrange it in such a way that we just remove that, you know, just subtract that constant from both sides. So if our, let's say that our constraint is something like x squared is smaller than or equal to 5, then we can make it x squared minus 5 is smaller than or equal to 0. So this is not a generality loss in any way if we assume that it's of the form g of x is smaller than or equal to 0. And then there are functions, constraint functions, which are mandated to be equal to 0. So for instance, if we have x plus y equal to 2, then we can make that into a constraint function x plus y minus 2, which should be equal to 0. So we assume that all the constraints are expressed like this. In 5.1, so there our set, feasible set, is represented by these functions as follows. So we have some sequence of functions from 1 to m, some set of functions, and m functions, gi is of x is smaller than or equal to 0. And then we have some p, 1 to p, these functions, hj of x is equal to 0. And all of these constraints need to be satisfied for a point to be feasible. We'll look at some examples where there are usually two functions that are involved, or 2 or 3. I mean, if we're dealing with 3-dimensional problems, then you have to understand that if you have this first kind of this inequality constraint, you can think of it as an easy example of an inequality constraint might be like, let's say we have 2-dimensional space and we have x squared plus. So let's take a 2-dimensional space in which we're dealing with a circle. Let's say some kind of circle like this, right? And all the points inside this circle. Yeah, that's our feasible set. So we would express, let's say this has radius r, then it's this g of x is now x squared plus sorry, y squared minus r squared is more than or equal to 0. And if we have I mean, of course, I mean, we can move the center of the circle to somewhere by putting here x minus a and y minus b if it's at ab. But you know, you understand what this means. So we have this is the sort of a thing that happens. And then if we take these HJ functions, I mean, in one two-dimensional case, so this could be, usually when h of x is 0, it draws some kind of, it's some sort of a line that's drawn here. And if it's more general, if it's, if for example, if it's if it's a three-dimensional space, then we could have something like, I can't really draw this very well, but you know, I can't draw an actual ball, but you know, the surface x squared plus y squared plus z squared is minus r squared is equal to 0. So I can't really draw a circle, but you know, or a sphere, but the surface of this sphere would satisfy this x squared plus y squared plus z squared minus r squared is equal to 0. So that might be an example in three-dimensional space. It's some kind of a surface. And in two-dimensional space, of course, it's just a line. And in three-dimensional, four-dimensional space, it's, you know, very hard to picture what it looks like. But basically, you can think of this, that these G constraints, geometrically speaking, they carve out a region of the space, hopefully a convex region, but we can't be absolutely sure what that is. But some kind of region in the space is the one that satisfies each of these G constraints. And then some kind of a hypersurface satisfies this h of x equals 0. So if you think about dimensionality, for instance, then each of these constraints doesn't drop the dimensionality of the space, it just carves out the region. But each of these constraints, these, you know, it drops the dimension of the space by 1, because then you have to have this equality constraint satisfied. So in three-dimensional space, these would be like surfaces, and in more two-dimensional space, these would be curves, and so forth. So we have both of these kind of constraints at play here, and we have to figure out what to do when these constraints are at play. We can transform this into vector notation. So if we have these h constraints, we can just say that any x must satisfy that this h of x vector is 0, and then this g of x vector contains only components smaller than or equal to 0. So this is, we can think of the general constraint problem as being in this format. So now we know what it looks like, and you know, we assume that this objective function and the constraint functions are all continuously differentiable. Like I say, continuously differentiable in the sense that if there may be points where they are not differentiable, at least the derivative is not continuous, but those points are only, you know, you can easily detect them, and they're numbered, so we can deal with those. There are situations where constraint minimization problems don't have solutions. It's fairly easy to come up with a constraint problem which has no solution. So for instance, if you're dealing with f of x such that it's x when x is between 0 and 1, and it's 1 when x is equal to 0. So this is not a continuous function. So if it's not continuous, then it's very, very easy to generate situations where it's not, where it doesn't have a solution. There is one thing why we want this to be true, you know, continuity and minimize problems and so forth. So we have what is called a compact set. Now a compact set is, we'll look into what that compact set means, but for now, it's not exactly equivalent, but for now, just for this purpose, instead of compact, think that it's closed and bounded. So technically speaking, those two imply compactness. Compactness is a little bit more general property, but for our purposes, actually, we look at compact sets that are guaranteed to be closed and bounded. And by closed, we mean that if it has an edge, the edge is sharp and is contained in the set. And if it's bounded, it means that in the space, when we go to a point of the set, then we cannot go in any direction. There is no direction where we could go infinitely long and still find points of the set. So there is a bound. Basically, it means that somewhere in this space, if it's like I said, compactness is not the same as closed as bounded, but for our purposes, think closed and bounded. So if it's closed and bounded, then it has a sharp edge, and you can basically draw a circle that is guaranteed to contain all the points in this set. A finite circle that is guaranteed to contain all the points in this set. So if those conditions are met and our function is continuous, then it has a minimum and a maximum value in this set. So the only thing we need to do is to find it. And to find it is not easy, obviously. It being continuously differentiable helps. It being convex, and more importantly, the set being convex, makes it actually easy. So let's look at these situations. We can derive what are called the necessary conditions for the minimum. Necessary means that if we have guaranteed that everything is continuous and differentiable, then we know, for instance, that we're dealing with a closed set. Then the optimum point is either at the edge of the closed set, or it is a place where the derivative is 0, right? So the problem here is, of course, that the constraints that we deal with, we assume now there are functions h of x is equal to 0 and g of x is smaller than or equal to 0. They can produce pathological situations that make it hard for us to have a generic result that says, okay, this kind of points, look at these kind of points, they're going to be the optimal. So we will derive a certain set of conditions under which the optimum can be found, but we cannot guarantee that this works unless certain properties of these constraints are satisfied. So we'll take a look at that next. So let's assume now, we call these constraint qualifications. So we have to assume certain things like continuity, differentiability, continuity of the derivatives, a lot of non-pathological situations that we also have to explain shortly. But if you think just your normal intuitive functions, then I'm going to explain these conditions. If they're for normal non-pathological functions or non-pathological situations, these so-called KKT conditions, or Karush, Kuhn, and Tucker conditions, I just call them KKT for short, or KKT points for short. And this guarantees that if we're dealing with regular non-problematic problems, we'll shortly show what that means, then a minimum point is guaranteed to satisfy this condition. And it looks cryptic, but let's go through it piece by piece, what it means, okay? And I'm going to try my best to make sure that you understand what it is. It looks horrible. It looks horrible, but I'm going to draw a picture which I hope will help you understand. Okay? So I wonder if I could make this bigger myself, this my own picture here. Here. The problem is I don't know how to make my own picture bigger here. Well, okay, you can look at my picture. I can't see it myself bigger, but let me just give an example of a situation. So I have here a two-dimensional space because I can't really draw I could try to draw a three-dimensional picture, but it's going to look ugly, let alone a higher dimensional picture. I can't draw those. So let me just say that this is, this line here is g of x is equal to 0. And then this region, so this line here is a line where g of x is equal to 0, and everything inside this is g of x is smaller than or equal to 0, right? And then I have this curve. I have this curve here that says h of x is 0. So now here, my feasible set is basically all the points on this line extending from here to there. Okay? All right. And I'm going to do it. I'm going to just mark the ends of this line. So those dotted places are the places that are mark the end of that's the edge point, and that's the edge point. And all the points here, those are the feasible points because they must satisfy that g of x is smaller than or equal to 0 and that h of x is 0. So let's look at the points at which we might have the optimum. Obviously, the optimum might be here all along this line, or it might be here at this h of x is equal to 0. It may be, maybe there. I could probably draw this in an even more general way, in such a way that it may even end up in a situation where we have a line that stops here and then everything to the left of it is 0, right? It could happen like this, so that I can draw that situation as well. So here's my g of x smaller than or equal to 0. And then I have here so I could have a situation like this. H of x is 0 here, and then it reaches it's 0 here, and then everywhere to the on this region it's also 0. I could have a situation like this as well, just as well. I mean, think about a function whose value depends on x and y, but if x is 0, it's all smaller than or equal to 0, it's always 0, for instance. Something like this. It could happen. Never mind that. So what kind of points are we considering optimal? Obviously, we might want to look for the derivative of, or the gradient of, if we are just in a region, if we're somewhere in a region like this, where there's no equality constraint, so we can move around freely. And we're not near the edge of this region. If we are somewhere in here, and the optimum is, let's say, there. Let's say that's our x star. If the optimum is there, then we're not near the edge here. G of x is definitely smaller than or equal to 0, and h of x is 0 because it's 0 always in here. then the only thing that we need to, then this might be a local optimum if the gradient of f, the cost function, is 0. So if the gradient of f is equal to 0, and then, we have to be able to find these numbers, these coefficients, something times, something's greater than or is equal to 0, and then some coefficient that is a real number. Well, in that case, we're nowhere near the edge of this, this region, and let's say g of x is smaller than or equal to 0 at that point, and h of x is 0 at that point. And we can just, basically what we can do is we can ignore these, and these constraints allow us to ignore it. We choose these mu of x, mu of I, we choose all of them to be 0. We choose all of these lambdas to be 0. So we can completely disregard this part. We can completely disregard this part. The gradient is 0, right? And mu I times g of I is 0. Satisfied? Fine. G of I at x star is smaller than or equal to 0. It's feasible. And h of x is 0 for all of those h's. So it satisfies. So this definition obviously covers the situation where we are in the middle of some feasible region. We could move in any direction, right? And the function has a gradient of 0 at that point. Okay, that's fine. Let's take another look at the situation. Let's say that the minimum is here at the edge where g of, it's here. Let's say that this is my minimum. G of x, not, this is Ix star. We are at the edge of such a region. So the gradient need not be 0 now. It could be, but maybe it's not. The h of x conditions, they don't matter now, because h of x is 0 and it's 0 no matter where we move. So we can just make these coefficients, these lambda coefficients, be equal to 0. Okay, we can forget about this h of x. Okay, so, but now, what does this g of x mean? Well, let's look at this very closely. Think about this region here, and let's zoom in. I'm going to draw another picture in which I'm zooming this in a very, very, and I'm making this, so this shaded region, so here, look at this. So this shaded region is the feasible region, and this white region is where we cannot go. Now, let's think about this for a moment. Where in here can we go? We can go here either sideways, moving along the line, or we can move inwards into the region, but we cannot move in that direction. So that if it's an optimum point, then any point, any direction where we are allowed to go has to be a direction in which the function would only increase, right? So this means basically that our gradient of f, needs to point directly here inside. Why? Why does it have to point directly inside? Can anyone answer? It's continuous and differentiable. Let me draw another picture just as a question for you guys. Let's say that here is the region's edge, right? That shaded region is the inside. And let's say that the gradient points in, let's say that the gradient points like this. And let's say it's continuously differentiable. Then what can we do? What can we do to make this function just a little bit smaller? Remember the definition of the Gateau derivative. And remember how the function behaves with respect to the derivative. The thing is, let's move in this h direction just a little bit. What is the dot product between the gradient and this h? Because here the angle is more than 90 degrees, then what is the dot product here? What is the sign of the dot product? Anyone? Well, if you take the dot product and if it's an acute angle, then the dot product between vectors that are in acute angle is positive, right? If they point in the same direction, it's definitely positive. And if they're orthogonal, the angle is a right angle, then it's 0. And if it's is that obtuse angle, so if they point more than 90 degrees, then the dot product is negative. And remember that the Gateau derivative, the directional derivative, is the dot product of the vector that the direction we want to go and the gradient. So what this means is that if this is continuously differentiable, then if we go, I'm just going to draw this is the line that is orthogonal. This line here is orthogonal to this gradient. So if we go anywhere to the north of this line, then we will be able to go at least a little bit in that direction to make this function smaller. And because there are feasible points on this side of the line, then there is a possibility of finding smaller points even if we go just a little bit in this direction. But if this thing happens so that this points directly inwards, this gradient, then all the directions in which we can make this function smaller are here. And that's what we require of the optimum, is that if we are on the edge here, then all the directions where we can go inwards into this region or along the edge of this region must be increased directions, meaning the dot product with the gradient must be positive. So in this case, what is the gradient of G? The gradient of G, because remember, this inwards area is where G of x is smaller than 0. On this line, it's equal to 0. And on this outward area, it's larger than or equal to 0. So the gradient points in an orthogonal way to the tangent of this edge of the region where G of x is equal to 0. So the gradient of f and the gradient of G must point in opposite directions. Meaning the gradient of the gradient of f is some constant times the gradient of G. This constant being negative, obviously, if it's that constant. So in other words, if we write this, I'll just write this. There is a positive constant such that if we move it in this way, the gradient of f plus some positive constant times the gradient of G must be equal to 0. So that covers this first part. Obviously, we can have several different constraint functions, and maybe they intersect at that point. So the gradients point like this, and the inward, I mean, if we have, the gradients may point like this, the gradients of G1, G2, and then, the gradient of f must point somewhere inside the region so that we can decrease the function only by going outside of the region. That's the interpretation of this part. And then now let's include the h part here. So now the alternative is if we are along this line, if we are inside here, and let's forget about this g part here now. Let's forget about these now. Let's look at this h only. Then if we are on this line, then if the gradient of f, so let me draw another picture. So if I just zoom in, if we are on this line, and we are only allowed to move along this line, right? So if we draw a tangent of this line, I'm just going to exaggerate it a little bit. Let's say we draw a tangent of this line. So infinitesimally, when we zoom into this point, then we can only move along this line. And if it just so happens that the gradient of f if the gradient of f and the tangent here have even a little bit of angle in any other direction except the right angle here, then if the gradient points here, then we can move in this direction just a little bit at least to make the function a little bit smaller. So if we are to find the optimum, then at the optimum point, the gradient of f, and the tangent must be in a right angle, right? They must be orthogonal. And what about the gradient of h? Well, we know that h of x is 0 on here. So it's going to increase in either that direction or that direction. Doesn't matter which direction it's going to be increasing. In one direction, it decreases, and the other direction, it increases. The directional derivative of h of x is equal to 0 on this line. The directional derivative must be 0 in the direction of the line because h of x, while we are moving along this line, is maintained at a constant value. It doesn't change when we move along this line. So if h is differentiable, continuously differentiable, the directional derivative must be 0 into the direction where the line is moving at all times, when we're moving along the line. So this means that maybe, I'm going to draw here, maybe the gradient of h may point in the same direction or the opposite direction. The point is that it must have the same angle to this tangent as the gradient. And hence, we have that the gradient of f plus some constant lambda times the gradient of h is 0, right? So they point in either the same or the opposite direction. And now this lambda can be, this can be zero, negative or positive. It doesn't really matter. It can be 0 too. Why? Because maybe, just maybe, the gradient is exactly 0 along that line. And in that case, it's obviously you know, a point to look at. Well, this, when we take into consideration both the g and the h in here, that's the situation where we are on the edge and on the point where the edge and the line meet. And this simply states that, you know, the directions where we can go if this is where the line and the edge meet in here, then we can only move along this line inwards. And these coefficients will then satisfy the fact that, you know, the inwards directions must be such that the function will increase. So this simply analytically, or in this calculus manner, it defines the points along this line and the edge points or the middle points, how they relate to the gradient of f, in which direction can you go. So I urge you here to think of this in terms of the directional derivative, and then think that you have a certain set of directions in which you can move. You can move in the direction where h of x still remains 0. So the directional derivative of h must be 0 into the direction where you go. As long as you are inside the region, so g of x is not equal to 0, it is strictly smaller than 0, then the gradient of g doesn't really matter if you are moving just a little bit. That means that this is the condition here. The mu I times g of I is 0. So you can, when g of I is not equal to 0, so because we are feasible, it's smaller than 0. So it's strictly smaller than 0. So there is at least a little bit room to move before g of x is actually 0. So that this mu I can be taken as 0. One of them is 0. It says that either you are on the edge or you ignore that condition completely. And then if you're ignoring all the edge conditions, this simply states that the rooms, the directions into which you can move must be increased directions for f, or cannot be decreased directions. All right. I hope this clarifies the KKT conditions a little bit. So let's look at certain situations where this KKT conditions happen. I'm not sure. Let's take a quick poll here. Who knows the concept of Lagrange multipliers? Who knows the Lagrangian, the method of finding a minimum using the Lagrangian? Okay, well, it doesn't really matter. Yeah, that's good. Someone's voted no. If someone has seen the Lagrangian or discussed it, then you can vote yes. But it doesn't matter. I mean, most people either have or haven't. Doesn't really matter in this case. These constraints, these lambda constraints, are often called Lagrange multipliers. In a situation when these mu conditions or these g conditions, these inequality constraints do not exist. If there are no inequality constraints, these multipliers are often called the Lagrange multipliers. We'll see some examples in the exercises next week on pure Lagrangian methods. So if you are familiar with the Lagrange methods, then this reduces the finding of the KKT conditions points amounts to solving the Lagrangian when we have no inequality constraints. Here it's explained fairly easily. Well, not easily, but we can rewrite this in this kind of format, vector format, so that the gradient condition can be expressed as linear algebraic. So we have this mu vector, we have this lambda vector, this G prime, which is we take to be a matrix, the Jacobian matrix of this G function, which is vector valued functions, and this H functions Jacobian, which is again the matrix of this H function times the lambda vector. We can express this in these terms as well. It doesn't really matter. We didn't talk about the constraint qualifications. I said here that if these functions are not badly behaving, I'll show some examples or certain qualifications when this is met. When can we do this? There are situations where we run into trouble, and we need to look at those situations separately. What it means is basically that there may be points at which the functions behave badly enough so that there may be a minimum somewhere that does not satisfy these conditions. If no such point exists where this bad behavior is exhibited, then the optimum is found by just enumerating the KKT conditions and looking at them as to whether they are the optimum. So here are certain situations when we use these optimization algorithms. So I'm going to explain later strategies of how to make use of this idea in transforming this problem into an unconstrained problem. An alternative strategy, basically there are two alternative strategies for solving a problem that can be solved with these KKT conditions. There are two alternative strategies. One, we transform these G and H functions into functions that make it easier for us to run an unconstrained problem, because when we are going to violate, making sure that if we violate any of these conditions, then the cost function will be very large. For instance, we incur a penalty when these functions are violated. Sorry, these constraints are violated, making it very costly to be in a point that is not a feasible point, and then iteratively increasing the penalty and then looking at where we converge and deducing what the point is. And then maybe checking that that's a KKT point later by hand or by some other means. That's basically what we can do. The alternative strategy is to relax these conditions and then introduce an approximative condition and transform this into a linear linear programming problem, solve that, then find out which constraints are violated, add new linear constraints, and do this iteratively until we end up in a point that we can prove is a KKT point. So those are basically the possible strategies we can do to do this, make use of this, these things that we've learned already. No direct way of navigating through the KKT points. It's usually done in this way. Yeah. We say that this inequality constraint is active when it's at the limit. So G of X must be smaller than or equal to 0. We say that it's active at a point where it's 0. So we say that active, meaning that when we are here, as long as we are here and there is room to move towards the edge, then we can ignore the edge. It's a passive constraint. It doesn't constrain us until such a time as we are at the edge here. When we are at the edge, then it says that stop, we cannot move in this direction anymore, so you can only go in that direction. We say that it's active when we are at the edge. Otherwise, we say that it's inactive, meaning, again, we need this concept of openness or you know, well, okay, not openness, but if we think of this as inactive, then you can think of the neighborhood of a point, because as long as it's inactive, then there exists some neighborhood of the point at which it's still inactive, so that there in every direction otherwise permissible we can move, and this particular constraint doesn't affect us. At least we can move a little bit. We haven't specified what these constraint qualifications are. There are several ways of coming up with constraint qualifications. They're overlapping in the sense that certain set of conditions and another set of conditions may produce radically different situations. So this may produce certain situations where some of these other conditions are not met, or these conditions may produce situations where these other first conditions are not met, but both of them may be sufficient. It's fairly easy, sorry, it's fairly hard, it's not easy to give, well, I'd say it's impossible to give the sort of necessary and sufficient conditions. We can give strict conditions that says, as long as these are met, everything is fine. But then there will be situations where they are not met, but we could still do with KKT conditions. So let's look at the situations. Firstly, there are two possible situations. One, if we have a feasible solution of the minimization problem, then the theorem holds if the solution is a feasible point, then it can be found among the KKT conditions if A, all the functions are convex, the G functions are convex, and the linear constraint, and the equality constraints are linear constraints. So basically it's a linear programming problem added with some inequality constraints with convex functions. Then we know that the optimum is found among the KKT points, right? The other possibility is that if the feasible solution, if the solution point, the optimum point, is a point where all the gradients of these inequality constraints for active inequality constraints, if all the gradients of those constraint functions and those gradients of the equality constraints are linearly independent. Let me give an example of a situation where they might not be linearly independent. We will have in the exercises as well, but let me give an example of a situation where they might not be linearly independent. So let me just say that this feasible region looks like, let's say that the feasible region looks like this. I mean, just drawing something like this. And then let me draw another set of constraint that looks like this. And then this is the feasible. So let's say that this is the feasible region. Okay. Now we have a problematic point. The problematic point is over there. The problematic point is over there because the tangent of this constraint points in that, sorry, not the tangent, well, the tangents are pointing in the same direction, and the gradients of these functions point in opposite directions. They're not linearly independent at that point. Sorry, no, they don't point in opposite directions. They point in the same direction. So they point in the same direction in that. So these two constraints are not linearly independent in this point. That may result in a problem in which this point is not a KKT point, but it might be an optimum. There are other situations that have this B thing. So yeah, we have to have one of these conditions satisfied. Then there's theorem 5.5. If our feasible set is defined only via equality constraints, and we have an optimum point X star. It says that X star is a minimum point if x star is a minimum point, then there are these Lagrange multipliers exist. Okay, so it's very hard to say, but this requires, of course, that the hj of x are continuously differentiable. So let's look at this theorem 5.6. If we have a KKT point and all these functions are convex and these H constraints are, it says affine, but really it means that the equality constraints can be expressed as a linear constraint AX equal B. Then a KKT point in this situation is a global minimum. So it will have a unique KKT point. And the proof here, we can go through this. I'm not going to go in detail, but the proof is based on the fact that we can show that if we move from this x star to any feasible point x, then the gradient of f points, gradient of f gives us an approximation that this function must be increasing in that direction. And from the fact that f is convex, this means, and continuously differentiable, this will prove that, in fact, the function will increase. We don't know exactly how much it will increase, but it will increase. It is not decrease in that direction. So we already have proven this, that if we can show this, then it will increase. Convexity is used on the active constraints and the KKT point conditions, and then by just simple algebraic moving around of the terms, we can come to the conclusion that this gradient-based approximation of how does the value of f change when we move from x to x star is given by this part of the equation that is given with the g constraints, and due to the convexity of that and the nature of the KKT conditions, it's an increased direction for the function. It's fairly easy to understand when we just have the intuition of the picture that I drew here. Basically, this intuition of this pair of pictures. So this is a KKT point locally with this respect to this constraint, because the only places we can go are increased directions. This is not a KKT point because we can go in this direction. We can go in this direction to, we can go in this direction to make the function smaller, right? So we prove basically that if it's a KKT condition, then this thing holds, and there are no other problematic points because f is convex and the g functions are convex. Here's an example 5.7. It's really basically, this is the same example that I gave graphically about the inside point where the gradient is 0, and how this is a descent direction for this. So this is, I'm going to just, let's have a small break now. Let's look at this example 5.8. You can do it in your group. You can actually do this, go through this checking of the KKT points and checking of these coefficients. There are multiple stages here, so I urge you guys to go through the first 3. I'm going to divide you into what? Let's see, there are 10 of you. Okay, I'm going to divide you into 2 groups. And you have 15 minutes. Go through as many of these KKT condition points and see that, verify these results yourself by hand. problem 5.8. One of you in the group could actually pull up MATLAB and to just do these computations with MATLAB using MATLAB and see if you can or maybe a couple of you, and then see if you can replicate these results, find these conditions, solve these. It's not easy to solve this necessarily with MATLAB. I mean, we haven't taught this symbol, but if one of you is more versed in doing this symbolically, then fine. Otherwise, you can just check the computations that you get the zeros that you want. Check the first couple of these conditions, and we'll reconvene at 11:30, and we'll discuss these KKT points then. Recording. So when we transform this problem into this format where we have this G constraints, then we express them as x1 plus 3x2 minus 8 smaller than or equal to 0, and then 5x1 plus 2x2 minus 14 smaller than or equal to 0. And then this G3 of x is just minus x1. I mean, it's greater than 0, but we can express it as minus x1 smaller than or equal to 0. We could draw the picture here. It would be something like we would have, I mean, if we draw a picture of this and it's not fairly, well, we'll look at that exercises where you can do graphical representations of these, but really honestly, that I'm not going to do it in a very, how should I say? I'm not going to do it in a very accurate way, but you know, if we have these linear constraints, they're going to be looking like something like this. You know, I don't know. I have no idea. I didn't do this. So it looks something like this, something to the left of this line and to the below of this line. So maybe this would be the region. I don't know. I haven't done it for this, you know, graphically. And then you calculate the gradient and the Hessian. And you notice now that this Hessian, because x1 is greater than or equal to 0, you know that this Hessian is positive semi-definite. This is important, and we know that from theorem 5.1, we know that it's convex. So, sorry, we know that it's convex because positive semi-definite in the region. I mean, really only need to consider the feasible points. It can be non-convex somewhere else, but in this case, when we're dealing with the region where we are actually looking at this points, in that set, it's convex. So that's where it matters. And in this case, the Hessian is positive semi-definite because x1 is greater than or equal to 0, and it's a diagonal matrix, 6x1 and 4 on the diagonal, both being positive or non-negative at least. So it's positive semi-definite. It means that this function is convex in the feasible region. Now, we can use the theorem 5.6 to say that any KKT point is a global minimum, because these are constraints are convex. There are no linear constraints, these are convex. So we can look at these. The gradients of these constraints fairly easily constructed. I hope you did this. Formulate the KKT conditions. We notice that there is we can come up with these equations, and we can formulate this in vector format. Or we can formulate this in this, sorry, this is the vector format of the KKT conditions. So this latter part here are the facts that mu1 referring to the active constraints, so that the constraint function times mu1 must be 0. It means one of these is 0. Mu2 times the second constraint function, meaning that one of these is 0, and mu3 or x1 is 0. Now there are all these parameters are either positive or 0. So basically we have 8 cases to consider. All of them are 0, one of them is non-zero, 2 of them are non-zero, or all of them are non-zero, a total of 8 cases for different combinations. So the first one gives us x1 is 2 over square root of 3, x2 is 3 over 2. The second one gives us solutions and substitutions. We can go through here and we get points. But one of the things is that we get a contradiction, because when we solve for this mu1, we get a negative value. So the second one leads into contradictions. We can't solve it. It has no solutions that satisfy this situation. The third one.
Where you get the 27 in the step 2?
Let me see. Step 2.
Yes.
Let's see. Let's go through this. Did you run into trouble doing this? Did you get a different?
Yes, because there one equation there was 27 and we have no clue where we should to put this mu1 to get the 27x1.
Let's see. Mu1, let me just see here. Let's see. It's been a little while. It's been a year since I went through this, so let's see. Oh, sorry. Substituting into the second equation. The second equation would be, the second equation in this case would be 4x2 minus 6 plus mu1 times 3 is equal to 0. And solving from this, we get the solution was that mu1 is 4 minus 3x1 squared. So, yes, this is fascinating. Where does it come from? 27 times 4 x1. What is it? Let me see. Or do we have this 14 minus 4? I think it's multiplied by 3 all in all. So when we get 14, okay, 3 plus 3 mu1 equals 0. So I think there's a missing mid piece. So we get here substitution. I'll write this and I'll show it shortly. So we have 14 minus 4x over 3, x1 over 3, plus 12 minus 9. I'm getting a little bit weird situation here, minus 9 x1 squared. So when we substitute, we get this, right? And now I'm going to just rewrite this as multiply by 3 so this becomes 14 minus 4x1 plus 36 minus 3 times 9, that's 27x squared is equal to 0. So when you substitute this and you multiply it by 3 to get rid of this, then that's when you get this. And then you just rearrange this and multiply by minus 1. That's where it comes from. Okay? It's substituted here in this you're seeing this optimization, yes. So you substitute this in here in place of this, you get this. Then you multiply this whole thing by 3 to get rid of that, then you get this equation. And then you just multiply this by -1 and rearrange it, so you get this. Yeah, and now this is just a quadratic equation and you can solve for x1. It has two roots. This should be plus or minus, but because this minus can be taken out because it's negative and x1 must be greater than or equal to 0. And then we solve this mu1 from this equation, then we get mu is negative. So this is a contradiction. So it means that the second, look, make sure if you calculate these KKT conditions, there are several avenues by which you can start to solve them, because there are many different equations that arise. I mean, you just take them as single equations and solve them. You can come up with many. There are actually quite a few equations that come into play. And then some situations result in contradictions. So make sure that if you come up with a solution to the equation, that you check all the equations that you started from. For instance, here, there are a total of basically 5 equations. This first equation, first line of this gradient condition, the second line of the gradient condition, and all these three other conditions. And you may come up with several solutions. Some of them are contradictory, and some of them, contradictory in the sense that you have they contradict the actual constraints of the function, which are these. So also check that these constraints are satisfied. If some of these are violated by your solution, then obviously you cannot have a solution there. So this happens in the second one. And you do the third one. I'm not going to go through this. So the third one results in a contradiction. The fourth one results in contradiction. The fifth one results in contradiction. The sixth one should result in contradiction, as does the seventh one and the eighth one. But this is actually what should happen. Remember, we cannot have multiple, well, we could have multiple KKT conditions, but then the constraint, the cost function should be equal in all of them, because we had that this is convex. These conditions are convex because they're actually pretty much linear. And theorem 5.6 says that any KKT point should be a global minimum. So if we get two different KKT points and the function's value is different in these 2 points, then we have some problem. Something has gone wrong. So one bad thing about these kind of computations is that there are many equations to solve and many situations to look at. But the good thing about this is that there are many conditions to check against, so that it's fairly easy to come to check your answers. And you should check all the conditions in every prospected solution. I have several. There will be, I promise you that in the exam, there will be a question in which you have to calculate the KKT conditions of some problem. And very often the case is that if you only partially solve the equations, you come up with a point that seems like, okay, this is good. But some of the conditions are not met and it contradicts, and that point doesn't actually satisfy the conditions. So you have to check them, all the conditions really. Make sure that you check them all. Don't worry, we will rehearse this in the exercises. This week's exercise has a KKT point solution, so we will be looking at that very closely. Okay, so there were 8 cases, only one of them was feasible. So the constraint qualifications, I mentioned that they are there to make sure that if the constraints and the points all the points of your problem satisfy certain conditions, then the optimum is found among the KKT points. So here is a very simple example. Let's say that we are minimizing the distance from this point 1, 0 along this curve here. So we can express this as minimize x minus 1 plus y squared subject to x to the 3 plus y to the 2 is equal to 0. So this curve, this bird's peak kind of curve here it's a constraint that often is used. Similar constraints to this elliptic equations kind of are often used in order to show that there is a possibility of having pathological situations. So this is a case of those. So this bird's peak here, this origin here clearly is the closest to this 1, 0. And we will show that this does not satisfy the KKT conditions. And we'll have to see and figure out why and what is the problem here. Okay, so let's look at this KKT conditions now. Let's formulate them. So firstly, the gradient of the target function or the cost function is simply 2 times x minus 1 and 2 times y. Those are the components. And the gradient of the constraint, equality constraint, is fairly easy to formulate, 3x squared and 2y. And this should be equal to 0. You know, this, sorry, not this, the gradient plus lambda times the gradient of the constraint should be equal to 0, and also x squared plus y squared equal to 0 should be satisfied. Now, if we solve this and take this first equation, the gradient equation there, if we take the gradient equation, it simply says that either y is 0 or lambda is minus 1. We can try either one of those. And if y is 0, this gives us x equal to 0. But the problem is that if we look at this first component here, then this is contradicted, because if x is equal to 0, then 2 times x minus 1 is minus 2, and it is not equal to 0. So clearly, y equals 0, x equals 0 is the optimum. But in this case, it does not satisfy the KKT conditions. The question now before us is why? What is it in this problem that makes it a problem? And how can we detect this? How can we detect this? This doesn't explain what the problem is here. But let's look at the gradient of the equality constraint. Let's look at this part here. 3x squared 2y. What does it say? What there is a point. What is the value of the gradient at the origin? Well, it's 0, isn't it? Let's go back here. Here it comes down to linear independence. So look at theorem 5.4. The gradients, there are no inequality constraints. There's only a equality constraint, the h of x. And at origin, the gradient is 0. Remember, the gradients must be linearly independent. And that's really important to understand, that the set of vectors that contains only one vector, the 0 vector, is not linearly independent. It's weird. But the linearly independent set of vectors, you know, is defined as a set of vectors that if you add them together, you can only make 0 by multiplying all of them with 0, not with, I mean, you take a linear combination, the linear combination has to be 0 for the result to be 0. But if 0 is among those vectors, then you can multiply that with anything and it's still 0. So it's not linearly independent. And this is a case where that trivial thing happens. If you have one constraint, equality constraint, and that equality constraint function has a gradient equal to 0 at a point, then really, I mean, that point might be the optimum because we just don't know how, I mean, it's not going to be not necessarily going to show up as a KKT point. It might, but there's no guarantee that it shows up as a KKT point because the corresponding gradient here is 0, so that vanishes. So it may not satisfy the KKT conditions at all. Like in this case, example 5.9, it doesn't satisfy the KKT conditions at the origin, yet the origin is clearly the optimum point. And it's because the gradient of the equality constraint is 0. So it comes down to also, you know, you also have to check the points where the gradient of the inequality constraint is 0. Sorry, not inequality, equality constraint is 0. Because that's, remember, we had this thing like, I justified this thing that if you're moving along this curve, you look at the directional derivative and the directional derivative of the function and the directional derivative of this curve, you know, the function that defines this curve must be pointing in the same or the opposite direction, so that there is no, between this line and the gradient of the function, there is no angle, so that we can move along this line to make it smaller. And then there is, if there is a point where it makes this kind of a dent, it may be that the gradient of this this equality constraint function is 0 at the tip. So at that tip point, we just don't know. We just don't know how the function behaves if we move a little bit to the left or a little bit to the right on the curve. And that's why we need to check that tip point. And it is the tip point is the point where this h of x's gradient is 0. And this is what happens at this situation. All right. Next up, we will be looking at these equality constraints and specific cases where we only have equality constraints. This is going to be known as the Lagrange method. And this we can solve analytically. I'm not sure about you guys. I mean, I think the Lagrange method was in a very early stage of my mathematics studies. But, you know, if you're not familiar with it, then we'll learn it now, tomorrow. I think the origin comes from celestial mechanics or something. I think, I'm not 100% sure, but I think it may be. I may be wrong here, but I'll double check, or you can throw in the comments or something like this. But I think it was originally, Lagrange was doing something like celestial mechanics and looking at the, so after solving the equation for the trajectory of a planet or something, you know, solving for the perihelion and the aphelion or something like this. I don't remember what their names are. The closest and the furthest point from the sun, right? So I think that was where it came from, but I'm not 100% sure if this is where it was first used. But Lagrange was a French mathematician, and he came up with this method. All right. I think, am I mistaking him for Laplace? I think Laplace was doing something with celestial mechanics as well. But, you know, maybe Laplace, Lagrange, tomato, tomato. Okay. That's all for today. We'll continue with equality constraints. I'll stop the recording now. Just a second.